In this section, we study higher order homogeneous linear equations with constant coefficients. In the previous section, we did study some higher order linear equations, but their constants, the coefficients were not constants. If the constant coefficients are present, then um, we have an easier way of solving the equation because we can just extend the methods that we learned for solving second order homogeneous linear equations with constant coefficients, which we did in section 4.2. So what we do is we again write the auxiliary equation, solve it, and then for every distinct root r of the auxiliary equation, we add a term of the form CERT to the general solution. For every repeated root r of the auxiliary equation, um, which is repeated, say, k times, we add an expression of the form. So remember previously, we were just dealing with second order equations, so a root could be repeated only 2 times. So we had C1 plus C2t e to the RT. But if a root is repeated k times, which can happen in a higher order equation, then we again start with C1 plus C2t, and then we have plus C3t square, and we go on. We keep on raising the power of t with another constant. And the last power is ck. Last term is ck to the k minus 1, and all this multiplied with e to the rt, where r was the repeated root. So recall that if or note that if k is 2, which means it's repeated twice, so then this last term would be c2 t to the 2 minus 1, which is 1. So c2t, which is what this is. So if k is equal to 2 or root is repeated twice, then we just get what we are already familiar with, c1 plus c2t times e to the rt. And then similarly for every distinct complex conjugate pair of roots, a plus minus ib, in the auxiliary of the auxiliary equation, we add on an expression of the form c1 e to the at cos bt plus c2 e to the at sin bt, and that's exactly what we had in the second order case also. In the second order case, if this happens, and that's the only part of the solution, because only 2 roots are possible in the second order, and these two take care of it. But in a higher order equation, this could just be a part of the solution and not the full solution. But the idea is exactly the same. So let's consider an example. We have this third order equation, and we first write the auxiliary equation as before. So br cube minus 2r square. So r cube minus 2r square minus 15r is equal to 0. And here we can factor out an r. So if we factor out an r, we get r is factored, and okay. So from this one, if we factor in r, we will be left with r squared minus 2r minus 15. And now this one factors further into r minus 5 and r plus 3. So r minus 5, r plus 3. So we get r is equal to 0, 5, and negative 3. And therefore, they're real and distinct. All are real and distinct. So for each of them, we will add a term of the form CERT, where C is a constant. All roots are real and distinct. So solution is, so we'll have y is equal to, so let's call the first constant as a e0t plus be5t so be5t plus ce negative 3t. Okay, so e to the 0t is just e to the 0, which is 1. So this is just a times 1, which is a. So this first term is just a. So a plus be5t plus ce negative 3t. A plus be5t plus ce negative 3t. Let's write an uppercase C. I guess it doesn't matter. ce negative 3t Oh, they say X is the independent variable. So not T, nor previously, mostly we were dealing with T as the independent variable, but here X is the independent variable. Okay.